I want to talk about divergent series, but before I can do that, let's talk about convergent series. Let's suppose we have a series which converges, and what would that look like? Series look like an infinite sum. So here we'd have a0 plus a1 plus a2 plus a3, a4. And if it converges, then this infinite sum has a finite real value. And the trick here is, and this is hardly a proof, but it's just some intuition, that if we're adding up infinitely much stuff, right, that stuff better be getting smaller and smaller. The only way that this makes sense is if the dot dot dots are almost nothing after a certain point, right? Basically, what do we mean here? That means that these terms that we're adding up better be almost zero after a while. And that's what we can conclude. We can prove this mathematically if we want, but I won't do the rigorous proof. But if a series converges, then what does that mean for the dot dot dots to be basically nothing? That means that the things we're adding up, then the limit as n goes to infinity of the a_n's equals 0. All right, the things we're adding up better be almost nothing after a while. And that's the only way we can get this nice finite real number. Okay, so, but I said I want to talk about divergent series, and well, that just means we need to flip this on its head. If a series converges, then the limit of the sequence, all right, that's the thing we got to remember here, is that this is talking about the sequence within the series. All right, if a series, the whole sum, infinite sum, is finite, then the sequence shrunk down to 0. On the other hand, if the sequence, if the sequence of ANs fails to converge to 0, so it has to converge, and it has to converge specifically to the number 0, then the series could not converge. In fact, the series must diverge. This is mathematically, we call this the logical contrapositive. If P implies Q, then not Q implies not P. This has a special name when it's written like this. This is called the series divergence test. Other people call it the kth term or the nth term divergence test, but I like calling it the series divergence test because it can do one thing and one thing only. It can only tell me that a series diverges. All right, that's what it's used for. So show that certain very silly, actually, series diverge. They diverge really badly because the sequence didn't even converge to 0. And let's put this into action. All right, so take this particular series, and does it converge or does it diverge? And if it converges, what's its value? And here's the things that we're adding up don't look like proper fractions. I mean, they might be proper fractions, but they don't look like they're getting smaller and smaller. And I can do this because in my head I can sort of look at the limit as k goes to infinity here. But let's actually do this. Let's take the limit of the sequence. And let's compute that. We could do this lots of different ways. We could turn it to a real valued function and use L'Hopital, but probably easiest just to factor out the k squareds on the top and bottom. On the top we get 1 plus 3 over k squared. On the bottom we get 2 plus 1 over k plus 5 over k squared. And k squares cancel. Limit k to infinity, that gets us 1 plus 0 over 2 plus 0 plus 0, and that is 1/2. So the sequence converged, but that sure ain't 0. And remember, if we're going to add up these, infinitely many of these, we're basically adding up infinitely many 1/2s after a while, because as k gets really large, everything's basically 1/2. So if you add up infinitely many 1/2s, what's going to happen? You're not going to get anything finite. You're going to get something infinite. And that's where the series divergence test the series diverges. And since it diverges, it cannot have a value, so we don't even have to worry about this second part of the question. Okay, so it's something very important here to keep straight. The series divergence test, as I've said, only shows us when series diverge. They can never tell us that a series converges. And let me give you an example of why that is. Okay, let's take a look at a very famous series. So I'll define two things. I'll define the harmonic sequence, 1 over n from n equals 1 to infinity, and that's the numbers 1, 1/2, 1/3, 1/4, 1/5. And I don't have to tell you that that limits to 0. So it satisfies, or it doesn't satisfy the series divergence test. So the thing is, that does not immediately mean that the series converges, all right? So we took the limit as n goes to infinity, 1 over n, and that sure is 0. So the series divergence test, and let me put this in capital letters, doesn't apply. With some underlines, because someone's going to forget this, right? The only way you can apply the series divergence test is if the limit doesn't equal 0, or if the limit doesn't even exist. But as soon as you take that limit and it becomes 0, you got to give up and try something different, because the series divergence test just doesn't work if your limit of your sequence is 0. And in fact, this series does diverge. The harmonic series n equals 1 to infinity of 1 over n, that's 1 plus 1/2 plus 1/3 plus 1/4. Turns out it diverges. Even though its sequence converges to 0, there's a, clean that up there, it's supposed to be a 1. Even though the sequence gets smaller and smaller and goes to 0, the series still diverges. And here's a quick proof of that. We'll learn using a more powerful technique called the integration test. We can find a nicer way to show this diverges, but here's a cute way. If I'm adding 1 plus 1/2 plus 1/3 plus, eventually I'd get where to, well, of course 1/4 would be next, and then 1/5, and then eventually I get to 1/8. And I'm just going to look at the powers of 2 here, 1/9 through 1/16. All right, and that's probably enough. This is our infinite sum, and I'm going to do some clever grouping here. I'm going to do, here's a 1, here's a 1/2, and I'm going to group through 1/4, I'm going to group through 1/8, I'm going to group through 1/16. And I'm going to add each of these parentheses up. All right, so here's my 1 plus a 1/2. Oh, I'm not going to do that just yet, because that would be really nasty if I tried to add up all these numbers, right? But what I can do is I can make everything smaller. All right. So it's going to be greater than or equal to. Really, it's going to be greater than. And here we get the 1/3. I'm going to rewrite that as a 1/4, and that makes it smaller, right? 1/4 plus 1/4. And then everything in here, 1/5, 1/6, 1/7, I'm going to replace all those with 1/8. So how many of those would be? 5, 6, 7, 8. And here, I'll replace everything with 1/16. Okay, and then what do I get? I got 1 plus 1/2 plus, here I have 2/4, here I have 4/8, here I have, how many of these are there? There are 9, 10, 11, 12, 13, 14, 15, 16. There's 8/16. And maybe you see the pattern here. This is 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2. And that don't equal nothing. If it equaled anything, it'd be infinity. That diverges to infinity. We might say that. I don't like to say it equals infinity because infinity is not a real number. But here's the deal, right? If we have, and I'm basically using the direct comparison test, which is another series technique, but it kind of makes sense, right? If you're adding up a bunch of numbers, and that's bigger than a bunch of numbers that add up to basically infinity, well, sure, this guy is also basically going to be infinite as well. And so that's the idea of the proof. Not quite as rigorous as it could be, but that's the idea of the proof at least. And so that's why this harmonic series diverges.